What specific problem does the lmssSLUNG method aim to solve regarding language model training, and what are the key challenges it addresses compared to previous approaches?
The lmssSLUNG method aims to solve the problem of training language models to understand high-risk data, such as toxic or copyrighted content, without enabling them to generate such content. A key challenge it addresses is the inherent entanglement of understanding and generation in traditional next-token prediction objectives, which can lead to models inadvertently learning to produce harmful outputs. By introducing a selective loss mechanism that adjusts the training loss based on the risk level of each token, lmssSLUNG allows models to learn from high-risk contexts while preventing the generation of high-risk tokens. This contrasts with previous approaches that either filter out high-risk data, limiting model exposure, or rely on post-training methods that may not effectively suppress harmful generation. Ultimately, lmssSLUNG provides a framework for safely leveraging high-risk data to enhance model capabilities without compromising safety.
How does the proposed lmssSLUNG method work? Illustrate the steps involved in its methodology, particularly focusing on how it applies different loss functions based on token risk levels.
The lmssSLUNG method operates by introducing a selective loss paradigm that differentiates between high-risk and low-risk tokens during pre-training. Each token in a training document is labeled as either high-risk 1 or low-risk 0, based on its potential for generating undesirable content. For high-risk tokens, lmssSLUNG employs custom loss functions that either mask the loss, setting it to 0, or apply an unlikelihood loss, which penalizes the model for assigning high probabilities to these tokens, effectively preventing the model from learning to generate them. In contrast, low-risk tokens are trained using the standard maximum likelihood objective, allowing the model to learn to generate these tokens while still being conditioned on the context provided by high-risk tokens. This dual approach enables the model to understand and respond to high-risk content without the risk of generating it, thus achieving a balance between safety and capability.
Can you provide a simple yet illustrative example demonstrating how lmssSLUNG operates, particularly how it identifies and processes high-risk and low-risk tokens during training?
lmssSLUNG operates by categorizing tokens in a pre-training document into high-risk and low-risk based on their associated binary labels. For instance, if a token is identified as high-risk L_I equals 1, it is processed using a custom loss function that either masks its loss in masked lmssSLUNG or applies an unlikelihood loss in unlikelihood lmssSLUNG, effectively preventing the model from learning to generate that token. Conversely, low-risk tokens L_I equals 0 are trained using the standard next token prediction objective, allowing the model to learn to generate these tokens while still being conditioned on the context of high-risk tokens. This dual approach enables the model to understand and recognize high-risk content without generating it, as it can attend to high-risk tokens during the generation of low-risk tokens. For example, if a model encounters a high-risk token like toxic in a sequence, it can learn to recognize the context of toxicity while generating a non-toxic response, thereby achieving a balance between understanding and safe generation.
What are the theoretical and practical advantages of using lmssSLUNG over traditional data filtering methods in pre-training language models?
Theoretical advantages of using lmssSLUNG over traditional data filtering methods include its ability to decouple the understanding and generation capabilities of language models, allowing them to learn from high-risk data without generating it. This contrasts with filtering methods that discard high-risk content, which limits models' exposure and understanding of such data, ultimately hindering their performance in real-world scenarios. Practically, lmssSLUNG enhances a model's ability to recognize and respond to toxic content while minimizing the risk of generating harmful outputs, as demonstrated in the toxicity experiments where models trained with lmssSLUNG outperformed those trained solely on filtered data. Additionally, lmssSLUNG provides a flexible framework that can be adapted to various high-risk domains, such as copyrighted material, enabling models to engage with sensitive content without the risk of infringement. Overall, lmssSLUNG offers a more nuanced approach to training language models, balancing safety and capability effectively.
How was the lmssSLUNG method validated in the experiments, specifically detailing the datasets used, evaluation metrics, and the significance of the results achieved?
The lmssSLUNG method was validated through experiments involving two primary scenarios: toxicity and factual learning. For the toxicity evaluation, the model was continually pre-trained on toxic Reddit documents, with the effectiveness measured using the real toxicity prompts for generation and the civil comments dataset for understanding, employing AUROC as the evaluation metric. In the factual learning scenario, the TOFU dataset, consisting of synthetic author profiles, was used to assess the model's ability to answer questions without generating entity names, with performance evaluated based on the correctness of responses. The results demonstrated that both masked and unlikelihood lmssSLUNG variants achieved Pareto optimality, significantly improving understanding of toxicity while minimizing toxic generation compared to baselines, thus validating the effectiveness of the lmssSLUNG approach. Overall, the experiments highlighted that lmssSLUNG allows models to learn from high-risk data safely, achieving substantial improvements in understanding without compromising safety.
What limitations or challenges are associated with the lmssSLUNG method that may impact its implementation or effectiveness in broader applications?
The lmssSLUNG method, while innovative, faces several limitations that could impact its broader application. Firstly, the reliance on a span-level risk classifier to label tokens as high risk may introduce inaccuracies, as the effectiveness of the method is contingent on the classifier's precision in identifying toxic content. Additionally, the unlikelihood loss approach may lead to higher perplexity on non-toxic documents, potentially reducing the model's ability to generate coherent low-risk text in contexts associated with high-risk content. Furthermore, the method's performance in understanding and generating factual knowledge is tested primarily on synthetic datasets, which may not fully represent the complexities of real-world data. Lastly, while the method shows promise in toxicity understanding, it remains to be seen how well it generalizes across diverse high-risk domains beyond toxicity and factual learning, which could limit its applicability in varied contexts.